Hey there y'all, today we're going to look at 3.1 on functions and their representations. And so in this lesson you'll be able to determine if a relation is a function, and you'll also be able to determine how to convert between relations between different representations, including mapping diagrams, tables, graphs, and ordered pairs. The standards for this section, FIF1 and FIF9, dealing with what is a function and also the types of representations that we have. And so we first need to look at two definitions. And in these two definitions, we have that a relation is a set of inputs and outputs. Now, all that means is that we're dealing with two variables. One is the stuff that goes in, the other is the stuff that comes out. We might also see these terms as the independent and dependent variables. Okay? But what is a function? Well, a function is a relation, and so that's the term we just talked about there, a relation, where each input only has one output. And so we're going to show this in a couple of different ways. We're going to look at how this is represented. So there are 5 ways to represent a function, and we're going to look at them in this order. So first we're going to look at ordered pairs, then tables, mapping diagrams, graphing on the coordinate plane, and finally the equation of a relation or function. And so we're going to look at those in order and see how each one represents a relation or function, and which ones will be functions and which ones are not. And then we're going to look at how to switch between different ones. So let's look at ordered pairs first. So we have 2 examples here asking us, are these relations functions? And so when we look at ordered pairs, we're given the ordered pairs, and remember that the first of an ordered pair is always the x and then the y. So this is x and y and x and y and x and y. And so is this relation a function? Let's go back to the definition. The definition said that every x can only have what? One y. Now, negative 2 has 4, right? Negative 3 has 5. Negative 4 has 6. And negative 6 has 6. Now, this is okay. This is a function. Yes, it is a function because the definition says that every x can only have one y. The definition doesn't say that every x has to have a unique y. And so we're allowed to repeat y values along with different x's. Okay? Let's look at example 2. We have 1, 1, 2, 2, 3, 3, and 3, 4. Okay? Well, again, we have our x to our y, our x to our y, x to y, and x to y. Right? And so, do we have 1x to 1y? Right? Now, again, they don't have to be unique, but do I only have an x going to 1y, or do I have an x going to 2 y's? And that's what we see here. We see here that 3 goes to 3, but 3 also goes to 4. So this is not a function because x equals 3 has 2 y values. So again, if I have an x value that has more than one y value, it is not a function. All right, so let's go ahead and look at how we look at functions and relations in tables. So when we're given a table, it could be either horizontal like we see this one here with the x's on top and the y's on bottom, or it could be a vertical table like this with the x's on the left and the y's on the right. It doesn't matter which way we're given the table, we still need to look at the relationship of the x's to the y's and understand, does every x have just one y? And so we look here, negative 5 has 7, negative 4 has 8, negative 3 has 9, negative 2 has 10, and negative 1 has 11. None of my x is repeated, and so is this relation a function? Absolutely, yes. It is a function because every x had what? One y. That's all we need. Okay? Again, if we see the same x repeat with different y values, then we don't have a function. So let's look at our next one and looking at mapping diagrams. So in example 3 here, we're looking at a pair of mapping diagrams. And again, the question is this relation a function? And remember what we're talking about. We're saying, does every x only have one y? Well, look at what happens here. And these arrows will tell us what's happening. The 1 for x goes to 1 for y. The 2 for x goes to 4 for y. The 3 for x goes to 9, and the 4 for x goes to 9. Remember what we said back in example 1. I can have different x's go to the same y value. What I can't have is the same x go to different y values. And so this is yes, it is a function. Because every x has only one y. Again, every x has only one y, right? And so this is fine. But let's look at example B. Look at what we have here. We have 1 going to both 1 and 2. And we have 2 going to both 3 and 4. And so is this a function? No. It is not a function. Now, why is it not a function? Well, it's not a function because both x equals 1 and x equals 2 have 2 different y values. That's the key thing. So again, pay attention to what your x's are doing. And the easiest thing to do with a mapping diagram is look at the arrows. If I have 2 separate arrows come out of the same x value, it's not a function. Whereas we go back to example 1, I have 2 different x values going to the same y. That's okay. That is a function. All right, so we're going to go next to graphs and talk about those on if they are functions or not functions. So in example 4 here, we're looking at graphs of functions or graphs of relations and knowing if they are functions. And so when we see this line here, we see that a line, remember, is composed of infinitely many points along that line. Now, every single one of those points represents an ordered pair. So if I'm here, right, I'm at 1, 1. Or if I am here, I'm at 3, 7. And so we have to think to ourselves, is there any x value that I have more than one y value for? And in this case, the answer is no. So this is yes, it is a function. And why is it a function? Because every x only has one y. Now, what would a graph look like if it was not a function? Well, let's scroll down and look at example B. Look at this one here. Is this relation a function? Well, remember the definition. Every x can only have what? One y. But watch what happens when x is -1. I have a dot up here, and I have a dot down here. So I've got -1, comma, -4.8, and I've got -1, comma, +4.8. I have the same x value with 2 different y values. And so this is no. It is not a function. Because, that's what BC means, because at x equals -1, there are 2 different y values. That's the key. Again, if I can take any x value and see that it has more than one y value, it is not a function. Now, we have a test for this, and we're going to talk about this test a little bit here, and we'll talk about it more as we go through. But it's called the vertical line test. And so the vertical line test tells us that if I can draw a vertical line through the function and touch more than once, then it's not a function, right? So if I can draw a line, a vertical line, because it's called the vertical line test, right? If I can draw that vertical line through the relation and touch more than once, it is not a function. It only has to fail once, okay? If I come back up to example 1, if I draw that vertical line through, I can draw that vertical line anywhere. And it's never going to touch 2 points at the same time. Okay? So again, I can use that vertical line test to see if a graph is a function or not a function. Okay? So that is example 4. Let's look at example 5, equations. Now, things you need to look at with equations, a couple things to understand. For an equation in two variables to be a function, the following must be true. The equation needs to be solvable for y with an exponent of 1. So it needs to, in the end, say y equals and then something on the other side. And then for part B, we need to be able to input one x value and not produce two separate y values. And so we're going to look at a couple of examples where this may or may not happen. And so we got three equations that we're going to look at. And so in A, y is equal to 3x minus 5. Is there any x value that I can plug in here? Okay, first off, is it solved for y? Yes, it's already solved for y, right? So it's already solved for y, so is there any x value I can plug into this and get two separate y values at the same time? Like if I were to plug in 2, could I get the answer to be 5 and negative 3? No. When I plug in 2, I get 3 times 2 is 6, minus 5, y is equal to 1, right? And if I plug in 3 for x, I get 3 times 3 is 9, minus the 5 gives me 4. And so I get a function because every x has only one y. And it meets the rules, right? We were able to solve it for y with an exponent of 1, and when we try values in for x, we don't get any repeats, okay? So let's look at B. Watch what happens here. Y is equal to positive or negative square root of x. And so if I plug in, let's say 4 for x, right? And I say y is equal to positive or negative square root of 4. What's the square root of 4? Well, that's 2. Well, this little positive or negative sign in the front means that I have both signs. I have positive 2 and I have negative 2. So I have an x value that I substituted in, 4, that comes out to two separate values, both positive 2 and negative 2. And so this one is no. It is not a function. Because any positive x value will give two y values. Okay? So again, it's not a function because any positive x value that I substitute in here will give me two y values, one being positive and one being negative. So it's not a function. All right, C, let's look at this one. Y is equal to 4x squared plus 3x minus 1. Is this one a function? Well, it is solved for y with an exponent of 1. And if I substitute in x values, like let's say I substitute in 0, I get that y is equal to negative 1. Or if I substitute in 5, I'm going to get 5 times 5, that's 5 squared, so 25, times by 4 is 100, plus 3 times 5, that's 15, so I'm at 115, minus 1, that's 114. So can I plug in any x value and get a single y value? Yes. And so yes, it is a function. Okay, so that's the key thing there. Again, make sure you pay attention to, can you get this down to where every x only gives you what? One y. Again, they can repeat later on, right? So x being 2 can go to 5, x being 7 can go to 5. That's fine. It's just that I can't have a single x value give me two y values. That's not a function. Okay, so we're going to look at one more thing, and that's on converting between these forms. And so we're going to look at a couple examples here to wrap up this lesson. So on example 6, we're given this relation, and it is 1, 5, 2, 6, 3, 6, and 4, 5. So it's a set of ordered pairs. We've given 4 ordered pairs here. And we want to write it as a graph, a mapping diagram, and a table. Now we're not going to write the equation here because that's going to be a section that we'll do later on. We're actually going to look at that in section 4 and section 5, writing the equations of these, and we'll also look at that in unit 4. So we're not going to worry about that at this point. So I want to take these ordered pairs, and we can do this in any order. So let's go to the table first. So if I want to write a table, x, y. And so remember, the first number in an ordered pair is the x, and the second is the y. And so we have to keep these lined up. So 1 goes with 5, and then x, y. 2 goes with 6, x, y. 3 goes with 6, and then x, y. 4 goes with 5. Now again, this is a function because every x has what? One y. Again, it's okay that the y is repeated. It's not okay that the x's repeat with different y values. All right. Now, we can go to a graph. So we can graph this on the coordinate plane. So 1, 2, 3, 4. 1, 2, 3, 4, 5, and 6. And so we're going to plot these points on the coordinate plane. So 1, 5, 2, 6, 3, 6, and 4, 5. So again, we see these on the coordinate plane graphed out. We're not going to connect the dots at this point. We're just graphing the points that we are given. And we see that even if we try the vertical line test here, it would pass all those points and be okay. So again, this is the graph. Finally, the mapping diagram. And so in the mapping diagram, you're always going to draw two bubbles. Label the first one X and the second one Y. You're going to list all your X values in the X bubble, preferably in numerical order from least to greatest. Now, it doesn't have to be. You'll see some mapping diagrams that are out of order, but it's best if you keep it in order just for the sake of organization. And the other thing about mapping diagrams is you will never repeat a value in the same bubble. So if I have the same Y value like I do here, I'm only going to write 5 and 6. I'm not going to repeat values in a mapping diagram. Now my X value is 1, 2, 3, and 4. And so we're going to draw our lines from the X with an arrowhead going to the Y. And so 1 goes to what? 1 goes to 5. 2 goes to 6. 3 goes to 6. And 4 goes to 5. And so our arrows show us the relationship from the X to the Y. Okay? Got one last example we're going to look at here with these. In this one, we're given a mapping diagram. And we want to look at the other three. We want to see it as a graph, a table, and a set of ordered pairs. And so we're going to take this relation. And we can do it in any order. We can do the table first, the graph first, ordered pairs first. It doesn't matter. As long as we have one, we can convert to the other three pretty quickly. And so let's just write out the ordered pairs that we have. Well, 1 goes to what? 1. 1 also goes to 2. So we know right away this is not a function because I have two separate arrows coming out of 1. But that's okay. I can still write ordered pairs. I can still graph it. I can still put it on a table. My other ordered pairs, 2 goes to 3, and 2 goes to 4. And anytime we're writing our set of ordered pairs, we're going to use those fancy looking braces. And if you need help drawing those, talk to me in class and we'll talk about how to write those out the best you can. Okay? We're going to graph this up. So X is of 1 and 2, Y is going 1, 2, 3, and 4. And we're going to plot those points. So 1, 1, 1, 2, 2, 3, and 2, 4. And so we see that this would fail the vertical line test because it hits 2 points at the same time. Okay. Again, that's okay. We can graph relations all day long. It just is not a function. Finally, our table. X to Y, and we do the same thing. 1 goes to 1, 1 goes to 2, 2 goes to 3, and 2 goes to 4. And so again, we can convert between any of these forms very quickly, starting with any of them. Okay? So don't be afraid when we go through this and we're looking at converting these from one to another and you're given something different. So if you're given the graph, just list out the ordered pairs first, and then you can do the mapping and the table after that. Or write it as a table first, and then you could do the ordered pairs and the mapping after that. Or do the mapping first. It's your choice which order you do those in, and having to convert between one and the other. So that is this section on 3.1 on functions and their representations. Make sure you fill out your Google form, and I will catch y'all next time.